Hello, everyone. Thank you very much for watching my presentation. Today, I'd like to talk about highly backdrivable high reduction ratio gearboxes for robotic actuators. My name is Yasutaka Fujimoto from Yokohama National University, Japan. This movie shows the gearbox we have developed, which has very high efficient features. Here is the input side and here is the output side. The gear can be easily driven from the rotor side, as shown in this video. So conventionally, the robotic actuators are composed of high reduction ratio gearbox, such as harmonic drive and servo motor. There are a couple of problems when we use this configuration. First, there is a mismatch between the allowable input rotation speed of the gearbox and the maximum rotation speed of the servo motor. Second, energy regeneration is difficult because backdriving efficiency of the gearbox is not so high. Third, safety concern arises due to low backdrivability when applied to cooperative robots or wearable assist robots. So in this talk, I'd like to show a solution to resolve these problems. Okay. So this one is the conventional simple planetary gearbox, and this one is very common harmonic drive. And we also use a cycloid gearbox and a plan-centric cycloid gearbox for high payload applications. But we need to consider the compromise between a reduction ratio, torque capability, and efficiency and compactness. So these are a relationship trade-off. So we have proposed a reduction gearbox, so-called BDG, that is bilateral drive gear. This gear has very good natures, such as highly energy efficient and cost-effective using involved tooth shape profile. And the gear is very compact, and the gear can realize a very wide range of reduction ratio from 1/10 to 1/1000. And when we use these high energy efficient gearboxes, we can solve the three problems I mentioned in the previous slides. That is mismatch of input speeds, energy regeneration in backward driving, and backdrivability for safety. And also the rotor torque can be estimated by using the motor side information. So let's see the nature of post-transmission in high reduction ratio gearbox. This model is very simple one for describing the high reduction ratio. So the blue part is the primary parts driven by motor force. And in this picture, the blue parts can move horizontally. And here is the contact surface between the primary parts and the secondary parts. Secondary parts is shown in these gray parts, which can be moved vertically. And the angle phi represents the reduction ratio. Actually, the tangent phi corresponds to the reduction ratio. The speed can be reduced when the power transfer from blue parts to gray parts. The speed of the horizontal speed of the blue parts is here V1, and that can be reduced to V2 by multiplying tangent phi. And if there's a small friction on this contact surface, we can formulate the force balancing equations. And by solving these equations, we can find the increase of the force described by this equation. By using a force relationship and velocity relationship, we can formulate the forward driving efficiency. In this case, the force is applied to the motor side. So the efficiency can be determined by the reduction ratio tangent phi and friction coefficient on the contact surface mu. So when the force is applied from the rotor side, the similar formulation can be possible. The speed relationship doesn't change, and the direction of the friction force changes in opposite side, opposite direction. So according to this similar formula, we can have a equation for back driving efficiency eta b, which can be described by this equation. By using these two equations, forward driving efficiency and back driving efficiency, we can find the rough relationship between two efficiencies. By eliminating these terms from both equations, we can describe the relationship between backward driving efficiency and forward driving efficiency using this very simple formula. So if we plot these equations, we can find the relationship between two efficiencies. If the forward driving efficiency is less than 50%, the back driving efficiency becomes 0. That means the gear cannot back drivable. And if the forward efficiency is very high, we can say that the back driving efficiency is also high. So this one is the other aspect of the forward driving efficiency and back driving efficiency. So the term mu over tangent phi, if the mu friction coefficient is constant, and then if we increase the gear ratio, the forward driving efficiency drops hyperbolically, but the backward driving efficiency drops quickly, linearly drops. And at certain reduction ratio, the gear cannot be back drivable. So from this relationship, we aim to increase the forward driving efficiency as much as possible. And also from the simple two-mass system, we can derive a block diagram considering the friction, equivalent friction between primary parts and secondary parts. Here is the backlash between two parts. And also we need to consider the friction coefficient here. And so the block diagram becomes a bit complicated, but we can derive the equivalent inertia at input from input shaft in forward driving like this. Conventionally, the efficiency, forward driving efficiency is ignored for formulating this equivalent inertia. but we found that the secondary mass is affected by the water efficiency. Similar to this, the equivalent inertia from the output side, rotor side, can be described like this. And here we need to also consider the backdriving efficiency. So this efficiency affect the equivalent inertia. So the next we want to talk about the proposed gearbox, which is the so-called 3K compound planetary gearbox. The basic structure is like this. Here is the carrier, which carries planetary gears. The planetary gear in the first stage and second stage are connected. And the sun gear drive the planetary gear, first planetary gear. And the first ring gear is fixed to the frame, and second ring gear acts as the output of the gearbox. So in this animation, the sun gear is input for the gearbox, and the green output ring gear moves very slowly, so which can be used to as an output shaft. So this gearbox is a kind of differential gearbox, but it can be driven by this sun gear. Actually, this structure is not so new. The similar structure can be found very many literatures. In this work, we proposed a method to determine the number of teeth of gears and the profile shift coefficients in order to maximize the efficiency. And thanks to this configuration, the wide range of gear ratio is possible. Okay, so this equation shows the torque balance equation based on power flow. This torque balance equation can be derived from the kinematics of the gearbox, and we need to consider some basic efficiency between two gears. And when we consider this basic efficiency, we need to consider the power flow. Based on that power flow analysis, we can derive these equations. By solving these equations with respect to the output torque, we can derive the relationship between the input torque and output torque. And also, using the speed relationship, we can formulate the full total energy efficiency for the driving as shown in this equation. So I1 and I2 are the ratio of gear teeth. So in the case for the backward driving, a similar formulation can be possible. And here is the back driving efficiency equation. So using these two equations, we can maximize the efficiency by changing the number of teeth as well as the profile shift coefficient. That can be affected to the basic efficiencies of pair gears. So here is the formulation for the basic efficiencies. So because there is small slip between the two gears, and usually we can assume that the friction coefficient on the surface of the gears is around 0.1 to 0.2. The basic efficiency can be derived from the geometric parameters of gears. So here's one example. This basic efficiency between two gears can be formulated by some geometric parameters. Here, GS1 and GP1 are the number of teeth for some gear and plant gears. And this epsilon alpha is determined by some pressure angle. And the pressure angle is determined by center distance. And the center distance is determined by the profile shift coefficients. So this one is for the pair of planetary gear and the fastering gear. So when we change the profile shift coefficient x, the shape of a gear changes. So if the profile shift coefficient is negative, the gear has this kind of shape. Here is the involute curve, and here is a trochoid curve. So if the profile shift coefficient is positive, then the mainly the gear shape is composed of the involute curve. So this parameter can be used to maximize the efficiency. Finally, we can formulate the optimization problem with decision variables of the number of teeth and profile shift coefficient. The former variables are discrete one. We apply the brute force search for all of the combination of this and the number of teeth for 5 gears. And also the profile shift coefficients can be determined, and they are continuous variables. And also we need to consider the several constraints for formulating the whole planetary gearbox. So once we fix the number of teeth, the problem becomes a convex optimization problem. All 5 continuous variables can be determined by solving this convex optimization problem. So the efficiency has some maximum point at certain parameters in most cases. So we searched all of the combinations having the gear ratio between 1/50 to 1/400, and all dots represent the local minimum solutions. And at certain combination of the number of teeth of the gears, we have very good efficiencies. So these points at full can be used to design the gearbox. So here are several prototypes of the gearbox. So this one is a bit small type, and these 3 are almost the same shape but having different gear ratio. And the efficiency slightly drops when we increase the gear ratio. So we have measured the efficiencies of the actual prototyped gearbox, which has the 1/100 gear ratio. So these are another prototype. So this one is a very small one, having a diameter of 225 millimeter. and the reduction ratio is 120, having around 90% of the efficiency. And also, this one has very huge gear ratio. And the last one has a very special one, having through hole. So we fabricated a couple of gears, actually. So this table shows the specifications of prototypes. So the top gearbox has over 90% efficiencies, having very small reverse starting torque, which is only 33 millinewton meter. The bottom one has around 90% efficiencies and also having very small reverse driving torque. Compared to the harmonic drive, we achieved very good efficiencies. And here is the measured efficiency map using a test bench shown here. The gear has very flat characteristic in terms of the input speed and the load torque. And when the case of the back driving, the efficiency is very high. It's around 85% in this case. Contrary to this, for the efficiency of the harmonic gears is less than 90%. And this one is very high reduction ratio bilateral gear. The ratio is around 1/1000. It is still back drivable. We consider this gearbox having the possible application as valve actuators having a manual operation mode. Okay, so this is the another application to power exoskeleton. In this system, a total reduction ratio is around 400. The knee torque is estimated by the multi-encoder disturbance observer, and that value can be used to assist the exoskeleton. So this plot shows the comparison between the measured knee torque and estimated knee torque. We can achieve very accurate estimation of the torque applied to the system. So this block diagram shows that external torque estimator. We employ the multi-encoder disturbance observer using the motor encoder signal as well as the potential meter attached to the load shaft. Thanks to this estimator, we can realize very accurate estimation of knee torque. This is another application to the collaborative robot. We are now developing the actuator module, and the robot can be fully back driven. And this is fully passive motion. So the joints are easily driven by human force. And also we are now trying to reduce the backlash of the system. So we will apply a slightly deformable ring gears to machine gears without clearance, and we employ tiny space allowing deformation of ring gear. The space is located between case and the ring gear. So using this configuration, the BDD can be applicable to industrial robots. So actually, here is the preliminary experiments measuring the backlash. The amount of backlash is around 1 arc minutes. So it's enough small for in the industrial applications. Okay, and other solution for reducing the backlash is to introduce the roller transmission mechanisms. So we proposed the hybrid mechanism bilateral drive gear together with the roller transmission. So we impose the roller among the 3K gear train. So this one is the actual picture of the developed gear. So these are roller ring, and the small torque can be transferred using the roller without any backlash, and the big torque can be transmitted through the conventional gear. So we measure the lost motion of the system, which is around 1.2 arc minutes. It's very small. But this is only under the light load condition. So this is another solution for reducing the backlash. So in conclusion, we have developed a bilateral drive technology that is an optimal design method for 3K compound planetary gearboxes having very high forward and backward driving efficiencies. And also we have confirmed that the proposed gearbox achieved 90% efficiencies. So if you are interested in our gears, please, I'm happy, please, if you can refer, check the papers showing the bottom of this slide. Thank you very much for watching this video.